Last episode, we solved steady-state conduction temperature that stopped changing with time. But most real problems aren't steady. They're about what happens in between. How fast does a quenched steel part cool? How long before a machined component is safe to handle? These are transient problems, temperature changing with both position and time. By the end of this video, you'll solve transient conduction 4 different ways: the lumped capacitance method, the classical one-term Heisler approximation, an explicit finite difference solver, and an implicit one, and you'll validate every single one against the others. Here's the roadmap: the transient governing equation, the lumped capacitance method, the full plane wall solution by separation of variables, Heisler charts solved numerically, explicit finite differences and why stability matters, implicit finite differences and why they sidestep that limit, and validating every method against the others. Recall from episode 1, this is the general 1D heat diffusion equation, derived from an energy balance on a thin slice. Last time, we set the right-hand side to 0 for steady state. This time, we keep it. With constant properties and constant area, this simplifies to the second derivative in space being proportional to the first derivative in time. We define a new property, alpha, the thermal diffusivity, conductivity divided by density times specific heat. Its units are area per time. It measures how quickly a thermal disturbance spreads through a material, not just how well the material conducts. This is the transient heat conduction equation in its cleanest form. Notice it's now a partial differential equation in 2 variables, x and t. Solving it requires not just boundary conditions in space, but an initial condition in time too. We need an initial condition, the temperature everywhere in the wall at time 0, usually uniform at some initial temperature Ti. And boundary conditions, for this series, we'll use convective boundaries, both faces exposed to a fluid at temperature T infinity, with heat transfer coefficient H. This is the realistic case for quenching or cooling in air. Solving the full partial differential equation is overkill for small, highly conductive objects like a thermocouple bead, or a small steel ball being quenched. If conduction inside the object is fast compared to convection at its surface, the whole object cools almost uniformly. We can treat it as a single lump with one temperature. The energy balance is simple: heat leaving by convection from the surface area A equals the rate of internal energy decrease, where V is the object's volume. Both sides have units of watts. Separate the variables, temperature terms on one side, time on the other. Integrating both sides from the initial condition at t equals 0 gives a logarithm. Exponentiating gives the classic exponential decay toward the ambient temperature. Tau is the thermal time constant, the time for the temperature difference to fall to about 37% of its initial value. Bigger mass or specific heat means slower cooling, bigger H or surface area means faster cooling, exactly as you'd expect. The validity of this whole approach hinges on the Biot number, H times a characteristic length, over K. The characteristic length is volume over surface area. Physically, Biot number compares the resistance to conduction inside the object to the resistance to convection at its surface. When Biot is less than about 0.1, internal conduction is so much faster than surface convection that temperature gradients inside the object are negligible. The lumped assumption holds. Above that, we need the full spatial solution, which is where the rest of this video is headed. In code, compute the characteristic length, the Biot number to check validity, and tau. Then evaluate the exponential decay formula across a number py array of time values, one line, no loop needed, since number py broadcasts the formula across every element of t at once. The result is the exponential decay we derived, starting at 800 Kelvin, dropping toward the 25-degree ambient, with tau setting the pace. Above a Biot number of 0.1, we need the full spatial solution to the heat equation, not just the lumped approximation. Before we solve it, we rescale every quantity so the equation becomes as simple as possible. This isn't just convenience, it makes the result apply to any material and any wall thickness at once. Theta is dimensionless temperature, it's 1 at the start and 0 once the wall reaches the surrounding fluid temperature. X is position, scaled by the half-thickness L, so the centerline is x equals 0 and the surface is x equals 1. FO is the Fourier number, dimensionless time. And Bi is the same Biot number as before, now built using the half-thickness. Solve the theta definition for t, then differentiate with respect to time, the constant t infinity drops out. Next, use the Fourier number definition to swap a time derivative for a Fourier number derivative, by the chain rule. Combining those two steps gives us the original time derivative entirely in terms of theta and FO. Do the same for position x equals x times L, so each derivative with respect to x picks up a factor of 1 over L and a second derivative picks up 1 over L squared. Applying that twice to the temperature gradient gives the transformed spatial derivative. Drop both transformed derivatives into the original Fourier heat equation. Every term shares the same factor of Ti minus T infinity, alpha, over L squared, and since that factor is identical on both sides, it cancels completely. What's left is the dimensionless heat equation, no alpha, no L, no material properties at all. It's the same equation for every material and every wall thickness. Here's the key trick. We guess, and later confirm by checking it works, that the solution splits cleanly into a part F that depends only on position, and a part G that depends only on time. Differentiate the ansatz and plug both pieces into the dimensionless equation. Dividing everything by F times G completely separates the variables. A function of FO alone sits on the left, a function of X alone sits on the right. Since X and FO are independent, the only way that equality can hold for every X and every FO is if both sides equal the same constant. We call that constant minus lambda squared negative, so that the time part decays instead of blowing up, which is what physically has to happen as the wall cools. That single partial differential equation has collapsed into two ordinary ones, a first-order equation in time and a second-order equation in space. We can solve each one separately. This first-order equation separates immediately. Put every g on one side, every FO on the other, and integrate both sides. Exponentiating clears the logarithm and gives a clean exponential decay, and the bigger lambda is, the faster it decays. Rearranged, this is the familiar simple harmonic oscillator equation. Its characteristic equation has purely imaginary roots, plus or minus I lambda, and imaginary roots always mean the general solution is a combination of sine and cosine, with two constants left to pin down from the boundary conditions. Physically, no heat crosses the centerline by symmetry, so the temperature gradient there must be exactly 0. Differentiate f, evaluated at x equals 0, sine of 0 vanishes, cosine of 0 is 1, leaving just C2 times lambda. Setting that to 0 forces C2 itself to 0, since lambda can't be 0 without giving a trivial, no decay solution. The sine term is gone entirely, and combining what's left with the time solution gives this compact form. At the surface, conduction reaching the wall from inside must equal convection carrying it away. That's dimensionless Fourier's law matched to Newton's law of cooling. Differentiate theta, evaluate both sides at x equals 1, and set them equal. Every term carries the same factor of c1 times e to the minus lambda squared fo, so that factor cancels completely, leaving a clean relation between sine, cosine, and bi. Dividing through by cosine lambda gives the characteristic equation, lambda tangent lambda equals bi. This is transcendental, it can't be solved in closed form algebraically, and it has infinitely many roots, lambda 1, lambda 2, and so on, one for every possible mode of the temperature distribution. Zero slope at the insulated centerline on the left, the cosine curve sits flat there. It bows downward toward the convecting surface on the right, where heat is actually leaving the wall. That gold curve is the shape every one of these boundary conditions was built to produce. Every lambda n that solves the characteristic equation gives a valid building block solution. Because the heat equation in both boundary conditions are linear, any sum of these building blocks is also a valid solution, so the true general solution is the infinite sum over every mode, each with its own coefficient Cn still to be determined. The initial condition says the wall starts at a uniform temperature, theta equals 1 everywhere at Fo equals 0. Multiply both sides by cosine of lambda mx and integrate across the wall. Because these eigenfunctions are orthogonal, a standard Sturm-Liouville result for this kind of boundary value problem, every term in the infinite sum integrates to 0 except the one where n equals m, leaving a single clean equation for Cn. Both integrals are standard. The first is a direct antiderivative of cosine, the second uses the half-angle identity for cosine squared. Dividing one by the other and simplifying the fraction gives Cn in closed form, depending only on lambda n, which in turn depends only on Biot number. This is exactly the formula we'll use in Python, now fully derived rather than just handed to you. We now have the complete, exact solution and infinite sum over every eigenvalue. But the eigenvalues grow with n, roughly lambda n is about n minus 1/2 times pi, so lambda 2 squared is already several times lambda 1 squared. Since every term decays as e to the minus lambda n squared Fo, the second term and beyond die out far faster than the first. In practice, once Fourier number exceeds about 0.2, every term except the first has already decayed to under 2% of its initial size, so keeping just that first term is accurate to within 2%. This is the famous one-term approximation, and it's exactly what the Heisler charts plot. And C1 is just our derived formula with n equal to 1, depending only on lambda 1, which we get by solving the characteristic equation for the given Biot number. Before everyone had a computer on their desk, engineers solved the one-term approximation by reading it off a graph, a Heisler chart. One chart gave the midplane temperature versus Fourier number, for a family of curves, one per Biot number. A second chart corrected for position off the midplane. A third gave total heat transferred. Every one of those charts is just a picture of the same equation we derived, lambda tan lambda equals bi, combined with the one-term formula. We don't need the picture, we can solve the equation directly. This is a root-finding problem. For a given bi, find the lambda 1 that satisfies this equation. Scipy has exactly the tool for that. We define the characteristic equation as a function that's 0 at the root, and hand it to Brentq along with a bracket between 0 and pi over 2, since tangent has a vertical asymptote there, guaranteeing exactly one root in that interval. Brentq finds it to high precision in a handful of evaluations. Then C1 follows directly from the formula we derived. Looping over a few Biot numbers and plotting theta naught against Fourier number reproduces exactly the family of curves from the classic midplane Heisler chart. Higher by means faster cooling, since it represents stronger surface convection relative to internal conduction. The one-term approximation is exact for this simple geometry with constant properties. But real problems often have temperature-dependent properties, irregular shapes, or boundary conditions that don't have a clean eigenvalue equation. The finite difference machinery from episode 1 extends directly to time-dependent problems, and that's what generalizes to anything. Just like episode 1's central difference, we start from a Taylor expansion, but this time we only need the simplest version, truncated after the first derivative. Rearranged, this is the forward difference, the new temperature at node I, minus the current one, over the time step. It's first-order accurate, half as good as the central difference, but for time stepping, that's the standard trade-off for simplicity. Substitute the central difference stencil we already derived for the spatial second derivative, evaluated at the current known time level n. That's what makes this explicit. Every term on the right is already known. Solving for the new value gives the explicit update formula, with a grid-based Fourier number built from delta x instead of the wall's full half-thickness. Every interior node updates independently, directly from its neighbors at the old time step. At the center line, symmetry means the node's mirror image has the same temperature as its first interior neighbor. That folds the stencil into this form, with a factor of 2 since there's effectively a neighbor on both sides with the same value. At the surface, an energy balance on a half-control volume, the same technique from episode 1's governing equation derivation, just applied to one boundary cell, brings in a grid Biot number, h delta x over k, to account for convection carrying heat away. Look back at the update formula. The coefficient on TIN itself is 1 minus 2 FO. If FO exceeds 1/2, that coefficient goes negative, meaning a hotter neighbor would make this node colder next step. That's not physical, and in practice it causes the solution to oscillate wildly and blow up. Keeping FO at or below 1/2 keeps every coefficient non-negative and the scheme stable. This has a real practical cost. Refine your grid for better spatial accuracy, and the maximum stable time step shrinks with the square of that spacing. A finer mesh gets expensive fast. That's exactly the limitation the implicit method we'll see next doesn't have. In code, choose FO at or below 0.5 and back out the time step it implies. Each loop iteration updates every interior node with NumPy's vectorized slicing. No inner loop needed this time. Since every interior node uses the same formula, then the two boundary nodes get their special treatment afterward. One gotcha worth calling out explicitly: np.full inherits its data type from whatever value you give it. If t is written as a plain integer, the whole array becomes integers, and every fractional temperature update from then on silently truncates to a whole degree. Over thousands of time steps, that compounds into a badly wrong answer with no error message at all. Always pass type equals float explicitly for any array you'll be updating in a loop. Plotting snapshots at increasing time steps shows exactly the physics we'd expect. The surface cools fastest, since it's in direct contact with the cool environment, while the center lags behind, and given enough time, the whole wall settles toward the ambient temperature. The explicit method stability limit comes from evaluating the spatial stencil at the old, known time level. The fix, evaluated at the new, unknown time level instead. This is called backward Euler, or the fully implicit method. Same Taylor series building blocks as before, just the right-hand side is now written at time level n+1 instead of n. Rearranging puts every new time level unknown on the left. Notice the problem. TIN+1 now depends on its neighbors at n+1, which are themselves unknown. We can't update node by node anymore. We have to solve for every node simultaneously. exactly the sparse linear system approach from episode 1. Every node's equation becomes one row of a matrix A, exactly as before, except this time, A only has entries on the main diagonal and its two neighbors, since each node only connects to itself and its two spatial neighbors. That's a tridiagonal matrix, the simplest kind of sparse matrix there is. The boundary rows get their own equations, built the same way as the explicit boundary treatment, just with the unknowns now at the new time level too. Unlike the explicit method, this scheme is unconditionally stable, there's no FO limit. You can take a much larger time step without the solution blowing up. The trade-off is that very large time steps lose accuracy, and solving a system every step costs more per step than the explicit method's simple vectorized update. In practice, implicit methods usually still win overall, because you need far fewer, larger steps to cover the same physical time. Scipy's diags function builds the tridiagonal matrix directly from three arrays, the main diagonal and the two off-diagonals, which is far more direct than the general sparse assembly loop from episode 1, since we know exactly where every non-zero entry goes. The matrix itself never changes between steps, since FO is fixed, so in a real implementation you'd factorize it once and reuse that factorization, but even solving fresh every step, this is fast for a 1D problem. Even with FO equal to 2-4 times past the explicit method's stability limit, the implicit solution stays perfectly smooth and physical, just reaching the same kind of cooling profile in far fewer steps. Let's take one physical case, the same plane wall, same Biot number, and check the midplane temperature predicted by the one-term Heisler approximation, the explicit solver, and the implicit solver, all at the same instant in time. All three agree within a fraction of a percent, three completely different derivations, an infinite series analytical solution, a forward-marching explicit grid, and a simultaneous implicit solve, all landing on the same answer. That's strong evidence none of them have a bug. One more demonstration, let's deliberately violate the explicit stability limit and watch what happens, compared to the implicit method given the exact same oversized time step. With FO at 0.6, the explicit method oscillates and diverges within a handful of steps, exactly the unphysical behavior we predicted from the negative coefficient. The implicit method, given the exact same time step, produces a perfectly smooth, physical cooling curve. This is the practical payoff of everything we derived this episode. That's transient conduction from every angle, an exact lumped model, an exact series solution, and two different numerical schemes, all agreeing, all built from first principles, nothing taken on faith. Next episode, we combine both, 2D transient conduction, marching the 2D stencil from episode 1 forward in time with the implicit method from this one. If you've made it, you can find the link of full Python code in the description. And if you want to see more videos like this, please subscribe, and see you in episode 3.